Welcome back. Today we are exploring a paradigm shift in large language model REL reasoning, the ASTRO Framework. By design, standard LLMs operate purely autoaggressively. They generate text token by token, continually predicting the next word based on the context of the previous ones. While this is highly effective for general text generation, it presents a massive vulnerability in complex logical reasoning or mathematical proofs. A single hallucinated token or mathematical error early in the generation acts as a poison pill, propagating through the entire sequence and completely derailing the final answer. We need a way for models to catch their own mistakes. You might think the solution is simple, just prompt the model to double-check its work. However, researchers have uncovered the self-correction paradox. When you ask an LLM, "Are you sure?" or find the mistake, it frequently degrades accuracy. Models will often take a perfectly correct answer and hallucinate an error just to satisfy the prompt's implication that something is wrong. This happens because the model's generation capabilities and its verification capabilities are heavily entangled in the base weights. True, intrinsic self-correction is fundamentally difficult without an external ground truth signal to guide the model back on track. Enter the ASTRO framework. ASTRO stands for Aligning Self-Correction via Tree Search and Reinforcement Optimization. Instead of relying on a reactive, prompt-based band-aid, ASTRO natively trains the language model to explicitly halt, evaluate, critique, and self-correct its own reasoning during the generation process. It treats reasoning not as a simple string generation task, but as a proactive search problem over a highly structured state space. By embedding the draft, critique, and refine loop directly into the model's policy via RL, ASTRO unlocks robust, autonomous problem solving. The foundational shift in ASTRO is moving from a token-level Markov decision process to a step-level one. Instead of looking at individual subwords, we chunk the output into discrete, logical reasoning steps like a single mathematical equation or a single sentence of deductive logic. In this framework, the current state consists of the prompt and all previously verified steps. The action space is the generation of the next complete reasoning step. This coarse-grained approach vastly reduces the horizon length of the search problem, making it computationally feasible to backtrack. To execute this search, the model needs a reliable way to evaluate its own state. We use a process reward model, or PRM. Unlike an outcome reward model that only looks at the final answer to assign a score, a PRMM evaluates every single intermediate reasoning step. As the base policy drafts a new step, the PRM steps in as an auxiliary scorer, taking the current context and the newly proposed step and outputting a continuous reward signal that represents the validity of the logic. Under the hood, the PRM is usually a scalar head attached to the final hidden state of the language model. We map the raw logits from this head into correctness probabilities using a sigmoid function. In the AST pipeline, we establish a strict confidence threshold. If the PRM's probability score for a drafted step drops below this threshold, the system immediately flags a reasoning error. This early detection is the critical trigger mechanism that prevents the model from spiraling down a hallucinatory rabbit hole. Once we can score individual steps, reasoning transforms mathematically into a tree search problem. The initial prompt is the root node. Each valid reasoning step forms a branch to a new child node. When a step is flagged as incorrect, that branch is pruned. At inference time, instead of greedy decoding, ASTRO leverages algorithms like beam search to expand multiple candidate steps simultaneously, maintaining a frontier of the most promising reasoning paths based on their cumulative PRM scores. For even more rigorous exploration, ASTRO can employ Monte Carlo Tree Search, or MCTS. MCTS elegantly balances the exploitation of high-scoring paths with the exploration of untried reasoning branches, using the upper confidence bound applied to trees formula. During generation, the model conducts fast rollouts simulating the path all the way to a final answer to backpropagate value estimates to the intermediate nodes. This look-ahead capability ensures the model doesn't get trapped in greedy, local optima that ultimately lead to dead ends. When a step fails, the PRM threshold backtracking mechanics kick in. The model halts its forward generation, completely discards the invalid step, and reverts the state back to the last known verified node. This is a crucial concept in ASTRO, retreating to a safe state before attempting a correction. By explicitly removing the flawed logic from the context window, we ensure the model's subsequent attempts aren't contaminated by its own prior mistakes. After backtracking, the model activates its critic policy. Rather than blindly guessing again, the critic generates natural language critique tokens. It looks at the verified history and the discarded, failed step, and writes an explicit explanation of exactly why the logic failed. Was it an arithmetic error? A false assumption? By articulating the exact logical fallacy into the context window, the critic provides highly targeted, conditional guidance for the next generation phase. Next comes the refiner policy. The refiner takes the original state and the generated critique and proposes a brand new, revised step. This revised step is once again passed to the process reward model for scoring. If it passes, the tree search resumes moving forward. If it fails, the loop continues up to a maximum number of retrees. In practice, the draft, critic, and refiner policies are usually unified within the same language model, separated by specific system prompts or control tokens. To train this unified self-correction behavior, ASTRO utilizes direct preference optimization, or DPO. We build datasets of successful and failed correction trajectories. The DPO objective forces the model to increase the probability of successful self-corrections while heavily penalizing hallucinated corrections or double-down errors. The optimization ensures that the model's internal representations are aligned to prefer the mathematically valid refinement over just generating a superficially plausible but incorrect revision. Implementing ASTRO in PyTorch requires breaking away from standard Hugging Face utilities. You cannot simply call model.generate. Because we are making dynamic branching decisions at the step level, you must write a custom autoregressive loop. Within this loop, you explicitly manage the generation of step tokens, pausing to run the PRM forward pass, evaluating the threshold, and orchestrating the conditional switching between the draft, critic, and refine prompts. The most critical PyTorch optimization here is key-value cache management. When a step fails and you backtrack, you absolutely do not want to recompute the forward pass for the entire prompt history. Instead, you directly manipulate the past key values tuple. By slicing the key and value tensors along the sequence length dimension, you cleanly truncate cache back to the exact token where the valid state ended. Proper KV cache slicing reduces compute overhead during backtracking by orders of magnitude. During the reinforcement learning phase, the PyTorch training loop handles experience replay. You collect full rollout trajectories, both the successes and the pruned failures into a replay buffer. Using PPO or reinforce algorithms, you calculate advantages based on the PRM scores. The policy gradients are then backpropagated through the network to update the weights, iteratively tightening the model's ability to accurately critique and effectively refine its own outputs over time. One of the most exciting properties of ASTRO is its utilization of inference time compute. Unlike traditional models where compute is fixed by the context length, ASTRO scales performance with test time computation. By allowing the model more search iterations, wider beam widths, and more refinement attempts, accuracy scales logarithmically. The longer the model is allowed to think, search, and correct, the better its final performance on highly complex reasoning tasks. To rigorously evaluate this, we don't just look at standard accuracy. We measure pass at one with and without the self-correction loop engaged. More specifically, we track the correction success rate, or CSR. The CSR isolates the refiner's performance by measuring exactly how often a step flagged as incorrect is successfully converted into a valid step on the first retry. High CSR proves the model is truly reasoning, not just randomly sampling. To summarize, ASTRO bridges the gap between raw generative models and reliable autonomous agents. By shifting from reactive prompting to proactive state space search, integrating robust process reward models, and applying precise KV cache-controlled backtracking, we can train LLMs that genuinely catch and fix their own logical flaws. Integrating these techniques into your PyTorch pipelines is the frontier of unlocking the next level of mathematical and logical reasoning in AI. Thanks for watching.